today we're talking about oxidation numbers and the balancing of oxidation-reduction reactions. So to begin, we have oxidation numbers that we need to discuss. There's basically 7 rules of thumb or rules for what oxidation numbers are, and we're going to go through those first. But what is an oxidation number? An oxidation number is the charge an atom would have in a molecule or an ionic compound if electrons were completely transferred. So number 1, free elements, or just those elements in uncombined states, just elements by themselves, have an oxidation number of 0. Here's some examples, just some elements. Doesn't matter whether it's just a metal element or a non-metal kind of diatomic element. All of these have oxidation states of 0. Number 2, in monatomic ions, the oxidation number is the same as the charge on the ion. So what are monatomic ions? Single atom ions. So again, if we have metal ions, so lithium ion, because it's an ion, it's always a +1 charge because it's an alkali metal. Its charge is its oxidation number. The iron 3 ion has a +3 charge, and oxide is a -2 oxidation number. The oxidation number of oxygen is typically -2. However, in peroxide, this is hydrogen peroxide, but peroxide is an O2 with a 2- charge. It is a -1 oxidation state. Number 4, the oxidation number of hydrogen is a +1, except when it's bonded to metals and binary compounds. In these cases, its oxidation number is a -1. So if we had something like this, its name would be magnesium hydride, and magnesium is always a +2, which makes hydrogen a -1. And notice again its charge is its oxidation number. Okay? How come? It has gained electrons. Where does it gain those electrons from? From the magnesium. Number 5, group 1 metals, or alkali metals, are always +1. Group 2 metals, or alkaline earth metals, are always +2. And fluorine is always a -1. Notice this does not say halogens. All halogens have a -1 charge in compounds, but the oxidation state of fluorine is the only one who is always a -1. Number 6, the sum of the oxidation numbers of all the atoms in a molecule or ion is equal to the charge on the molecule or ion. So if we have a molecule, it's going to have a net charge of 0, so it's going to add up to 0, and whatever our ion charge is, all of our oxidation numbers need to add up to the charge on the ion. And then lastly, the oxidation numbers do not have to be integers. The oxidation number of oxygen in the superoxide ion, which I've never seen on any kind of AP test or anything else, it's in your book, so we'll cover it. It's not going to be on a test or quiz that you see from me, but it's O2 -1. So because there's 2 oxygens and its charge is -1, each of these oxygens must have a -1/2 oxidation number. Alright, so how does this really work? Oxidation numbers of all the elements in HCO3. So we know that hydrogens are typically a +1, or they're always a +1 unless they're with a metal. There's no metals here. So hydrogen is going to be a +1, and oxygens are typically -2. So if oxygen is -2 and there's 3 of them, it really contributes an overall -6. Hydrogen is a +1. So really we're going to have +1 plus x -6 equals, and the charge on this compound, or this ion, is a -1. So in this case, what does our oxidation state of carbon have to be? It needs to be a +4. And that's how you determine oxidation numbers. Here's a periodic table. Again, this is a figure right out of your textbook that says all of the possible oxidation numbers. And notice as we kind of go in the middle of our transition metals, we get more and more oxidation numbers, then fewer and fewer. Second, more and more, fewer and fewer. And kind of likewise over here when we get in the P block elements, it kind of peaks here in the middle, or this one kind of keeps on getting bigger, bigger, bigger. But there's kind of trends of, again, fluorine's the only halogen that's always a -1. The reds are what's most common, but again, this is a textbook in your, or a figure out of your textbook. There's no need to memorize all these. If you know the 7 rules we talked about in the previous slides, you'll be fine. Alright, so again, just some practice. Oxidation numbers of all the elements in the following. So I think if we look at this first one, sodium iodate. Sodium, because it's an alkali metal, is always a +1. Oxygen is typically a -2. So again, if sodium is a +1 and oxygens are -2 and there's 3 of them, that's -6. And this time it is a compound, so it's going to add up to 0. So what does X have to be? X has to be a +5. So iodine in this case is a +5 oxidation number. If we come up to this one, fluorines are always -7 or -1, and there's 7 of them, so it's -7. And this has to add up to 0. So in this case, our iodine is a +7. And then down here, potassium, it's an alkali metal, so it's a +1. Oxygen's typically -2. So again, if we have 7 oxygens, that is -14. And we have 2 potassiums, that's a +2. And now we're really going to go +2x equals 0 again. So we're going to find out that chromium in both these cases is a +6. So again, that is how you determine oxidation numbers. You should, if you're given a compound, you should know certain ones of them from our rules, and you'll typically have to determine the other. Alright, so electrical chemical processes are oxidation reduction reactions in which either the energy released by a spontaneous reaction is converted to electricity. That's basically what happens in a battery. You have several chemicals in a battery. They react with each other, and in the process they give off electrons, which we use their flow of electrons to actually run our electronic devices. Or electrical energy is used to cause a non-spontaneous reaction to occur. And this is essentially how rechargeable batteries work. Once all those electrons have moved, we plug them into a wall, and the electricity in the wall actually causes that battery, the electrons, to basically go backwards, and we kind of renew what chemicals we had to begin with. And then we take those batteries out of the charger, put them back in our electronic device, and they run again, just reusing the same electrons they had the first time. So if we have a reaction similar to this, this is just an overall chemical equation, but what is the oxidation state of this magnesium? It is a 0 because it's by itself. What is oxygen? It is 0 because it's by itself. So we just have elements non-combined. However, magnesium over here is a +2, and oxygen over here is a -2. Alright? And these add up to 0, which is the charge of our compound. So we can really break this up into 2 separate reactions. The first would be 2 magnesiums yield 2 Mg2+ ions, and then in order to balance this, because we have 2 magnesiums and 2 magnesium oxides in this compound over here, we have a +2 charge on the right and a neutral charge on the left. So in order to balance our charges, we would have to add 4 electrons on the right-hand side. And this type of reaction is called the oxidation half reaction. And this is when we lose electrons. The other type of half reaction we have is our other one, which we have O2 as our reactant on the left-hand side, and we're producing oxide ions. And again, we have a -2 charge on this side, but there's 2 oxygens, so we really have a 2 times -2, so a -4 charge. And on this side, we have a neutral charge again. So by adding electrons, because electrons are always negative, if we add 4 electrons, we balance our charge. And this half reaction is known as the reduction half reaction. And in reduction, we are gaining electrons. So notice in this equation we have oxygen, it's gaining 4 electrons, and it's turning into 2 oxides. In this reaction we have magnesium, and it is losing electrons. Alright, so it has this. On the right-hand side we have magnesium ion, and in the process it lost 4 electrons. So if you remember that Leo says grrr, because Leo is a lion, Leo says grrr, this lets you know that lose electrons oxidized, gain electrons reduced. Alright, so balancing redox equations. If we have the oxidation of Fe2+ to Fe3+ by dichromate in acid solution as a question, the first thing we're going to do is write the unbalanced equation for the reaction in ionic form. So for this particular reaction, it's going to look like this. We have Fe, and it is being oxidized. All right, so it's losing electrons. So really, its oxidation state is increasing. And on the other side of our reaction, we have dichromate, and this chromium ion must be being reduced. All right, so if we kind of look at oxidation states, our Fe is its charge, so +2, and this Fe is a +3. And then over here, oxygen, we have 7 of them, but oxygen is by itself a -2, but there's 7 of them, so really it's a -14. And this overall is a -2, so 2 times what -14 equals -2? Well, chromium in this case is a +6. And over here, chromium ion is a +3. So, part 2, separate the equation into 2 half reactions. So we're just going to put our, I don't know, it doesn't matter, we'll do oxidized reaction over here, oxidation reaction, and over here we'll do our reduction reaction. But again, this does not matter which side you do it on. So I always think in terms of reduction, because it's easy to think who's getting smaller or reduced from left to right. So if I look at this, iron's going from 2 to 3, it's getting bigger, so that's not being reduced. And then chromium is going from a +6 to a +3, so this must be my reduction reaction. So I'm going to go ahead and write Cr2O7, 2- is going to yield Cr3+. Okay? And for now, I'm going to add a 2 over here just to balance my chromiums. So my oxidation reaction must just be my irons. So I'm going to have Fe 2+ going to Fe 3+. Alright, step 3. Balance the atoms other than O and H in each half reaction. So we have one Fe, we have one Fe. Over here, I've already kind of balanced my CRs. So we have 2 CRs, we have 2 CRs. It says balance the atoms other than O's and H's. Alright? So next step, we are going to, for acids, or for reactions in acids, and notice this says an acid solution, for reactions in acid, add waters to balance O's, and add H pluses to balance the H's. Okay, so in this equation, there are no O's. But over here we have 7 O's. So in order to balance those 7 O's, we're going to add 7 waters. Okay? And now, so we have 2 chromiums, we have 2 chromiums, we have 7 O's, we have 7 O's, but now we've just added 7 times 2, 14 H's on the right-hand side. So we need to come back to this side and add 14 H pluses, which is completely fine because this is an acid solution, so we should have some H pluses floating around. Step 5. Add electrons to one side of each half reaction to balance the charges. So over here we have a +2 on the left, we have a +3 on the right. The only thing I can add is electrons. So if I add an electron over here, what's going to happen to my charge? Well, a -1 + 2 is going to make this side a +1, and a +1 does not equal a +3. So I'm going to actually add my electrons right here. And how many electrons do I need? I just need 1. So notice I have one Fe, I have one Fe. My total charge on the left-hand side is a +2, and my total charge on the right-hand side is a +3 minus 1 is a +2. So this half reaction is balanced. On my reduction half reaction, we just checked to make sure everything was balanced as far as elements goes. We have 14 H's, 14 H's, 2 CRs, 2 CRs, 7 O's, 7 O's. But now we need to look at charges. So on this side, we have 2 times +3, or really a +6 charge on this side, on the right side. Over here, we have 14 pluses minus 2, or really we have a +12. So what do we need to do on this side to make a +6? Well, we need to add 6 electrons. Alright? So the last thing, or not the last thing, but step number 6, is if necessary, equalize the number of electrons in the 2 half reactions by multiplying the half reactions by the appropriate coefficients. So, in this half reaction I have 6 electrons. In this half reaction I only have 1 electron. So I'm really going to multiply this entire equation by 6. And just like in math, we're going to distribute the 6 to our 2 iron ions and to our electron. So this will become 6 Fe plus 2 yields 6 Fe plus 3 plus 6 electrons. And then lastly, we're going to add our two half reactions and balance the final equation and just make sure everything is completely balanced. So down here on the bottom, I am going to do this just another ink. Do it in red. So I have 6 Fe 2 pluses. And then I'm going to start adding this stuff over here. So I've got 14 H pluses plus dichromate. And I'm just going to put this off to the front, plus my 6 electrons. Okay? And that all yields, I'm going to come back over here and grab my 6 electrons, plus my 6 Fe 3 pluses, or plus 3s, it doesn't matter which order you write that in, and then my 2 chromium 3 plus ions, and my 7 waters. Alright, so now we need to go back and make sure everything is balanced. Well, the first thing we can see is we have 6 electrons, 6 electrons. These end up canceling, so we're going to ignore those, or just cross them out. And then lastly, we need to verify that the number of atoms and charges are balanced. So we have 6 Fe's, we have 6 Fe's, we have 14 H's, we have 14 H's, we have 2 CR's, we have 2 CR's, we have 7 O's, we have 7 O's. And now we also need to check, which we haven't really done with balanced equations before, our charges. So we have 6 times 2 plus, or plus 2 Fe's, so we're going to have a plus 12 charge. And then we also have 14 H pluses, plus 14, and then we're going to have minus 2. So overall, this adds up to a plus 24. On our right side, we have 6 times 3 is plus 18, and 2 times plus 3 is plus 6, and this adds up to plus 24 as well. So everything is balanced. We lost our electrons, so we know that 6 electrons are transferred, and those are the electrons that are used for creating electrical energy. And then our oxidation states are balanced. Everything is good. The very last thing is if our reactions are in basic solutions. What we're going to do is the exact same thing we just did. Alright, so if I can remember this, I think we ended up having 6 Fe plus 3's plus, what do we have? Cr2O7 and 14 H pluses. Yields, I think it was 6 Fe 2 pluses plus 2 chromiums plus 7 waters. Or no. This was a plus 2 charge, and this was a plus 3 charge. Alright, so if this was in basic solution instead of in acidic solution, what would happen is we would add OH minus, so we would add 14 OH negatives, okay? And what is that going to become on this side? Well, it's going to become 14 waters. But just like in math class, if we add 14 OHs to the left side, we also have to add 14 OHs to the right-hand side. And then we can also simplify our waters. So because we have 7 waters over here, we can actually reduce this, and we'd end up with 7 waters on our reactant side and 14 hydroxides on our product side. So notice this happens in base because we have OHs left over, as opposed to the first one which had H pluses left over. Alright, and that is it for balancing redox equations. If you like this type of stuff, I apologize sincerely, but you're a geek, or a nerd, whichever one you think is more flattering. But it's tedious, but when you get done with it, it does give a sense of accomplishment, just like, yes. So if that's the way you feel, I apologize, but you're already in AP Chemistry, so you know you're kind of leaning towards geekiness, nerdiness anyways. Have a great night. We'll try to do some of these in class tomorrow, but that is it for the night.